Okay, yeah, so the first slide is, I usually have it for these talks. I think it's too trivial for this conference. So excuse me for talking about different ways to solve linear system. It's just to motivate the type of linear solvers that I'm going to talk about. And yeah, so usually I started like that. You want to solve a linear system. Why is it you just not invert and go home happy? Why people propose all different methods, direct and indirect, also methods which would explore the structure of the matrix somehow, like hierarchical solvers. And typically here people ask, what is that? And I'm sure that people know here, I've already heard at this conference about them. So it's amazing. So there are different solvers that you exploit the structure of the matrix, tries to decompose it into pieces and solve, tries to use something. I'm going to focus on iterative methods. And today already, Yudi was talking about GMRS, and I'm going to be talking about projection-based methods, which are actually gradient descents on linear system. They actually, it's a version of gradient descent. In particular, all that I'm going to talk about can be interpreted in the sketch and project framework. And actually, because will be interested in these corruptions, it's a simple instance of a sketch and project framework. But I wanted to give kind of a picture. I'm particularly interested in the methods which have light steps and geometric projection based, because I think they have a potential to explore the space as they go and learn something about linear system as they solve it, which can be used for different tasks, for example, in trying to understand which equations might be wrong. So in particular, I will be interested in the case when the system doesn't have a solution, and I will distinguish in the middle of the talk between when we just have a noise, so we could have a small, when it makes sense to solve in the least square sense, or when we have adversarial who came and maybe corrupted some part of the system. And here we need to assume something about the percentage of what this adversarial can corrupt, because if adversarial corrupted everything, we don't have anything to solve anymore. So that's corruptions. I will formalize it later. I will use how the methods actually explore the space to be able to identify these corruptions. And I will only focus on linear systems here, but I want to kind of propose that these ideas, like gradient descent, can go beyond just linear systems in general. So when you have light iterations, you have and you should explore the space around you to be able to identify problematic pieces. You have this flexibility of small pieces to look at them. That's the plan. And actually, so for this talk, I shifted gears a little bit. So I'll talk more about, in general, randomized iterative projection-based solvers and how it's connected to sketching. It will be kind of rhyme with what Corelli was talking in the morning and what Deanna was talking before. Some sort different, a little bit different sort of sketching. So I wanted to spend a bit more time on that. Then I'll discuss how noise is different from corruptions, define the problem, talk about the method which we proposed. And actually, here I don't believe I'll get to there, but if I get to there, it is a version of stochastic gradient descent, which is also proposed. That is the simple algorithm, which is in the so it's one of the simplest versions of the sketching project. And to explain it, I don't need all this machinery. This is the algorithm which was used in tomography by engineers 50, 70 years ago. And you can find it in the optimization book, probably. So you want to solve your linear system and you want to do it geometrically. You take an iterate, you take the first equation, you project. So this is a right angle, you project onto it by Pythagorean theorem. You have to be closer, or at least not farther from the solution than before. Then you take the second equation, the third, and so on. In this statement, you can, so the distance should go down somehow. It was really hard to quantify how it goes down because it also depends on the system, also depends on the order of equations which you take. Right? You can see that already here that if so from x1 to x2, I didn't make much progress towards the solution. My step size was small, and this side of the triangle was much bigger. From x2 to x3, I had a huge progress towards the solution. So not all the steps are equally useful, right? What I see, what doesn't happen, right? So this projector doesn't show the blocks. It's fine. So, yeah, okay. So it's supposed to be the blue region. So the big progress towards proving the guarantees for Kaczmarz was done by Stromer and Vershinin here in 2008. So the idea is simply to randomize with the next iterate. So you pick the next equation, the next hyperplane, the next equation at random and project. That is all the algorithm. This is just a projection onto next chosen hyperplane. Here, I just select them at uniform because I assume that the rows are normalized. There is a way that sampling, so the sampling of the next row should be proportional to the norm of the row. And this allows to quantify the convergence. Basically, this random choice, well, it takes out of the picture the order in which we sample, right? So the only thing that matters after that is the structure of the system. And another good feature of this thing is that, well, we can actually see from the properties of the left-hand side, what actually makes it harder or easier to solve, and we can quantify the intuition that from x1 to x2 we made a little progress, from x2 to x3 we made big progress. Very intuitively, the more orthogonal the hyperplanes are, the better we are, because the next step will be. So if I have two orthogonal hyperplanes, I will. So for example, here I would immediately find x star if they would be orthogonal. If the angle is small, then I have. So for example, if I would not have this line, I would jiggle for a long time between this bundle of similar hyperplanes. So this can be written in terms of spectral properties, actually condition number of the matrix A. And that's what is there in the convergence rate. So it's expected convergence rate. I actually have in the next slide the general idea of the proof, because I think it's so easy. It's a one-page proof. It's very cute and very informative as well. So I'm going to talk a little bit about it. But what we can see is precisely that. So because I assume that I normalize the rows, this is just the number of the rows in the system. There is nothing mysterious in the denominator. In the numerator, the small singular value can characterize what we can call coherence in this case. Coherence here is just the angles, scalar products between the hyperplanes. For example, if we would have a Gaussian matrix, your rows will be Gaussian dependent vectors. They will be almost orthogonal. And if you would have, for example, another case, you have just one vector repeated many times. But so to make it say full rank, you perturb it with a very small noise. So you essentially have the same vector perturbed with very small noise. It's almost rank one matrix, right? And so almost rank one matrix, small singular value will be really tiny. Convergence will be really slow. This is the case with the bundle. Okay, this is the slide where I talk a little bit about the proof, because so it doesn't have random matrix theory. It actually have just just randomization probabilistic argument. This is Pythagorean theorem written. So the idea, which will be also important for us later, is that to quantify the progress of the iterate from k-1 to k, it's quantified by the step size. It's precisely the distance between the previous and this iterate because of the right angle. And this can be written as a scalar product with the random vector, which is the normal to a kth hyperplane. And it's random because we sample the next hyperplane at random. And then it can be the expectation can be written. It's expectation of the discrete random variable. It's an average over samples, and it can be lower bounded by the small singular value of the matrix. That's simple. If you have non-uniform, again, non-uniform rows, then instead of 1 over m, we'll have sampling probability driving us to the same result. And one more. So please stop me at any moment if you have any questions, or I'll just continue. So this part is okay. So we don't want our matrix to be random. That's important for this class of algorithms. In principle, sometimes we could assume that the matrix is random, and I will do it at some point. But we do want our randomization to be in the method rather than in the data. However, sometimes it's informative to look what happens in the random case. In particular, here it can give us intuition why we actually like our model to be tall over determined. In principle, Kaczmarz method would converge for any matrix, but if the matrix is square, you can also, it's intuitive that it will be very slow to do it looking at each equation and project, you will do it many times. But if your system is overdetermined, and this is kind of a standard case when this can be applied, you don't really, so it is a streaming algorithm. You take equations one by one. If you have many of them and they are overdetermined, you don't even need to see them all. So actually inverting it, for example, will include this m, which is much larger than n, that you don't really need. And your number of iterations has nothing to do with the number of equations. It's only about ambient dimension. And we can see, for example, if the matrix was random. So we can see how it's related to the convergence rate as well. For Gaussian matrix, if it is tall enough, then the smallest singular value will be of the order of square root of m, the same in the top and the bottom, so you'll get a constant rate. And then there is a threshold once your matrix becomes square, and that's true, that smallest singular value become close to 0. So from square root of m it goes to 1 over square root of m. Small singular value for square matrices is much less asymptotically. So you will have much smaller convergence rates. You can also see there. And I put here non-asymptotic random matrix T results because this is where I came from, but you can see the same from Mashenko Pastor. I'm sure you can see the same from asymptotic loss. There is nothing particular why I'm writing this with high probability. This is because that's my background. This is just captures the intuition. So coherent rows with small angles result in slow convergence. And typically we want to use it in significantly overdetermined systems. What does it do with the sketch and project? Well, we saw sketching before. I just want to argue first thing, if you don't do least squares at the moment, you solve linear system. Principal sketching is, well, it's trivial. If you want to solve a system, well, of course, you can multiply left-hand side and right-hand side by the same matrix. It doesn't change your solutions. There is a catch, of course, if your S is very small. So if it's a very wide matrix, you had one solution, but now you don't have enough information. You could have many solutions. But that's kind of the reason you want your sketch matrix to be small, so that now you want to solve smaller system. It's non-trivial when the smaller system is actually have more than one solution. So of course, if you sketch well enough and make a square matrix, you can just solve it directly. What people try to do, people try to make them smaller. So each particular subsystem has many solutions. So that's kind of a difference with randomized SVD, because here we don't stop after one sketch. We don't hope that one sketch will capture all the important information. We want our sketches to be of any size. And what matters is distribution of our sketches. Distribution of our sketches actually should explore the whole range of the matrix A. So that is what is different. So the following happens: each matrix sampled from a certain distribution, and the update rule would be, well, to find the best solution in certain norm for some sketched system which has more than one solution. So there is a great paper by Gaur and Richterek called something sketch and project. I think sketch and project is not in the title, but it's what introduces that method. There are 6 different ways to view the same thing. So you can, in particular, so 2 which are most important for us. This is optimization type. We find the minimum is the same as to project onto the X star plus null space of the sketched matrix. So we take a sketch, we project in the null space, we take another sketch, we project in that null space, and so on. This is a sketch and project method. We can do projection to different norm. This is why it's B right there. We can use different sketching matrices. Okay. Why do I talk about this suddenly? Why did I jump from Kaczmarz to that? Well, because Kaczmarz is a particular example of this. Can someone guess what should I do to get Kaczmarz from here? What should be my sketch? So Kaczmarz take one row of the matrix, right? So one row of the matrix and projects onto it. So what should be my S to actually select a row? Should be sketch of size 1, because I have one row which has 1, 1, another 0. So it will select me a row. That's that. Or we could do identity matrix doubled with zeros if I don't want to restrict myself by if I want size f. So this will be block Kaczmarz. This means that it will sample the sub block of the matrix and tries to solve the sub block of matrix of the matrix. And of course, as I said, Kaczmarz was known from, so it was randomized in 2008. Block Kaczmarz was proposed by Deanna Needell and Will Swartworth. After that, I have a date somewhere. So this sketching project framework is, it doesn't propose block Kaczmarz, it proposes a unified view because you can also write coordinate descent this way. You can write other methods this way, varying where you project actually. So the norm, so to write coordinate descent this way, you must project not in the Euclidean norm, but in the norm defined by the matrix A transpose A, basically. So you can encode many methods like that. And also it gives you a framework allowing you to think what happens if sketches were different, right? How it all depends. That's block Kaczmarz method, which I said. So if you just do it for a block, the iterate will be like that. You can, this is then sketch is just selection. So as I said, it existed before sketching project, and it's quite, so the initial analysis of that is quite connected to, for example, Haddock conjecture, because like randomized Kaczmarz depends on the condition number. Block Kaczmarz will depend on the condition number of all these sub blocks. How it was proposed to do by Needell and Trapp is to do splitting of the matrix into blocks with good condition numbers. And so what we want to be able to split into blocks so that each of them is well conditioned, approximately as well conditioned as the full matrix. If the matrix was Gaussian, random splitting will work. If the matrix was not Gaussian, we still could do that. And it was, so actually it was, so we want a constructive procedure. So even though Haddock conjecture is proved, I don't think it's constructive even now. So the solution which was proposed in one of the papers by Trapp, column subset selection, so on, is a constructive algorithm which does that up to a log factor. But so it finds to you a submatrix of particular size, which is almost as well conditioned as the full one. And then you repeat the procedure. This is how you can do a paving, so-called paving. Huh? What's the end result? So do I have it here? No, I probably don't have it here. So the end result will be, okay, so all the convergence rates look like that. 1 minus rho, where rho is this rate. So rho was this condition number, small singular value over Frobenius norm. And for the block thing, it will have operator norm instead of Frobenius norm on the bottom times log. So if condition on the fact that you have optimal paving, which in practice, you want search for that. Okay, so I don't think you would search for that because many things will work. People do randomize, or people try to, yeah. That gives improvement. So you do need to be careful because also each iteration becomes heavier when you take the block bigger. So this is one particular reason why analyze. So block Kaczmarz works very well, much quicker than regular Kaczmarz on consistent systems. One of the points of when I will talk about corruptions is that it's not a unique solution. If you have something else going on, like corruptions, or when you want to solve linear inequalities this way, you don't always want to project into blocks. You might be not robust. But if you just have a consistent system, you should do block Kaczmarz. However, it's harder to quantify the improvement of it precisely because to prove it, you need good paving and you lose the connection with the block size. So we did the work analyzing the same thing when your sketch matrix is Gaussian. In practice, of course, sketching with Gaussian is much heavier than doing blocks. However, it's a thing which it's much nicer to analyze, and we can get a rate which is lower bound by something which actually grows with sketch size. And now we can allow theoretically any sketch size. We can see how it grows with the sketch size. We also, okay, this is the theoretical slide. So here, what I want to show is that this is an interesting question, mathematical question by itself, because you need to estimate the spectrum, small singular value of sketch projected matrix. which is interesting by itself. And your S can be different. So for example, simplest thing is Gaussian, but you would like to sparsify, you would like to have count matrix there or something else. I forgot to put the date. So Stefan, who's in the room, he has, so among real relevant papers to here, what I mean here is that you don't only need, so small singular value will be your rate in the long run, basically. So when you start convergence, depending on your start, you have a faster convergence depending on other singular values. So there is a reason to actually look at the full spectrum, not only in the smallest singular value of that. That excuses the name that I'm saying that, okay, we want spectral properties. In principle, it's interesting to look not only in the smallest singular value there, but also on the full spectrum, although in the limit, smallest singular value will drive that. So originally in the original analysis, so what we did, we decoupled basically, we decoupled this matrix and used matrix deviation inequality with Gaussian width and so on. Gaussian width on this ellipsis is Frobenius norm. That's why I have combination between Frobenius norm and the square root of S operator norm in the bottom. That is not the best way to do it. And so this is not up yet, but this is what we're working on now, and it should be up like soon, within a month. We actually do like more refined analysis on that matrix right now, which will allow sparser samples. It will allow full spectrum analysis for, in some cases, it will also refine that. So removing this fact. So basically refine the denominator a little bit. So there is better things you can do in terms of random matrix theory there if you don't just decouple and treat them separately. Although even the first, so this result is very, but I think it's probably will be the most general in terms of the sketch size I can allow. I just proved it for Gaussian before. It can be extended to some sub-Gaussian sketches, even in the paper which has existed. So there is interesting stuff going on. And one more question I think is very relevant here is that, okay, this is a lower bound, but I'm actually interested in the rate and what is the gap? And yes, there is a gap, however, experimentally. So I intentionally didn't put what models I have here. Basically, these are matrices with different spectral decays. And dashed and solid lines are respectively rates, and expected this thing when I generated many matrices and took average and took small singular value. We can see that there is a gap, but we expect some constant. We expect constant factor here. However, they follow the same trend, and growth here with the, so basically the growth with change in sketch size, they mimic each other. They mimic each other here, and the purple one, when it grows faster than linearly, they also mimic each other. So it's it's quite nice estimates you can get from these things. Finally, okay, I don't have that much time. I'll talk about corruptions now. So happy to talk about that more. So noise versus corruptions. Okay, so here before now, I just talked about overdetermined but consistent linear systems. It might be too much to ask. So in the framework, when people don't have exact solution, but might have some noise, so that it makes sense to ask for least square problems. So it's 2 norm here. People thought about it. So actually, with each method I mentioned before, randomized Kaczmarz, block Kaczmarz, Gaussian, sketched Kaczmarz, me and Deanna Needell, we all did some estimate for noisy case in terms of the size of the noise. Right, I have it in here. So in the original Kaczmarz, it's Deanna Needell's paper. This is in the same Needell and Trop. This is in ours. So it depends on how optimal it is. So this is a bit better because it's 2 norm, that is infinity norm. I don't want to focus on that. What matters is that we have additional term, which always depends on the size of the noise, either infinity norm or 2 norm. What it also means is that if you run it on this problem, it won't converge to the point. It does converge to convergence horizon and starts bouncing around. And that's not very surprising, because if you have the system of equations which does not intersect at one point, and they keep projecting once you're in this region between all of them, I don't draw anything very, you keep bouncing between them here. You don't really know what to do. Actually, there is a new paper by Marshall Micklin that, well, they schedule the step size which goes through the noise. So you can do, by playing with the step size, you can do a bit better. It's not the focus of the talk, There are things you can do to go through the noise. Typically, you don't. In any case, both going through the noise and all that cannot do anything when you have an adversarial who came, take one equation, completely scraped the right-hand side and wrote a different number, which can be a million away. So least square solution will be very far. You don't learn anything, but you, especially in the overdetermined case, you should be able to recover the solution. If it's just one problematic equation, you still have overdetermined system, which is good. That's a corruption framework when you don't want to learn least square solutions, so you actually want to adapt your method somehow. This is about the sketching actually. So in the sparse corruptions case, your block Kaczmarz can spike, but sketching Gaussian kind of mixes the errors. It's more predictable, but it doesn't go to zero, so it's not good. So you do need to adapt the method rather than run one of them. That's the framework. You have so okay. So if you have one of them, one of the equations corrupted, yeah, I should be able to do that. But what is maximal you can allow? So if you have one half of equations corrupted by adversarial, it can just create its own system and you don't know which one is better. So the maximum you can hope for is a fraction of the entries. So here the remark is, so we do corrupt the right-hand side here. We do not corrupt the left-hand side. I'm happy to talk about like that a little bit more, but we do corrupt right-hand side, which is actually what differs these kind of questions from robust statistics where people usually corrupt the labels. So there is different things you can do. So there was the idea that you actually should look around, you should look what you can learn from the iteration was before us, was in a paper by Needell and Haddock on the 18th. They actually ran the Kaczmarz as it was, look at, so until it goes close to the solution, and then the intuition was if you have a corruption, it must be farther from your iterate than true equations, if you're close to the solution. So you just run it, then see whatever is far, you say it's corruption. It works if you can almost converge. If you have one half or like 1/3 of corruptions, every third step is corrupted, you don't really converge, so you don't enjoy that. So this is what so the methods which I explain in the next thing. Next slide goes when typical RK doesn't go. That is the theorem, but let me talk about the method. So the method does this. The method looks at the residuals. So okay, so the main intuition is the following. I kind of said it, but here I do it. So when you stay somewhere, you're in some iterate, you have additional information. Your additional information is distance from your iterate to hyperplanes. You don't know the solution, but you do know how far each hyperplane is from where you are right now. Right? There are methods even for uncorrupted Kaczmarz that say the following. So to do the biggest progress toward the solution, you want your step size to be big. So if you look at the residual, you want to go in the direction of the largest residual. This is Motzkin's method. It is slow, so you don't, when you solve the system, you probably don't want to look at each residual. It's like you better invert. But when you have corruptions and you don't know how to solve it, it's a different story because you can't just invert. You really need to see what's going on and what's wrong. So you can afford to look at the all like subsample of corruptions, and the intuition is that if you have something corrupted, it tends to be far, but not really. Sometimes it can be close like this. However, if it is close, these distances are not only indicator of potential corruption, but also your step size. So if it is small, even if it's corrupted, then go in that direction might be not that problematic. So you can afford that. So that's why statistics of absolute values of residual can be decisive. So for example, here we look at all of them. These two are too long. So the longest, so we don't consider them, but then we sample an equation out of green ones, out of shorter ones. That is quantile RK. And another way to do it is this quantile GD, which I'm sure I want to talk about it more. But what you also can do, you can also use this residual information to decide on the step size. So instead of that, you can do the following. You can, so in that case, you just ban these two projections. Here, you don't ban anything, but you don't go full project. Your step size in the directional projection is defined by the quantile of the residual. So so these are my residuals. So this is kind of a middle size of the residual, these two greens. That's why here, this is my step size. So my direction can be wrong, but on average, so it's my step size is governed by the residual. In both cases, we can prove that if you have a fraction of residuals, actually, we do need this fraction for the proof. We do need it to be small enough fraction. However, it's proportional to the size of equations. We have convergence, which is convergence rate up to a constant, the same as just for uncorrupted randomized Kaczmarz. We assume something about the model, namely we assume, for example, subgaussianity, and that's why the condition number is 1/n. And I will talk, this is main thing to talk in the last 5 minutes, what we assume about the model and why. Yeah, so we do need to choose this quantile. It has the same rate. The corrupted entries and values may be chosen completely adversarially. So another thing which we need, and we need our system to be overdetermined enough. If we don't have overdeterminacy, then we can't corrupt equations. So we just don't even have a solution then. If we have enough overdeterminacy, then it works. The bigger aspect ratio, the better it is. But for the size, so this is all negative. So size of corruptions doesn't matter. And sometimes it only helps. So what do we want from the model? And there are, I think this is maybe another very interesting thing here. We formulated this as a random matrix model for the matrix, which differs from how randomized Kaczmarz was done in the beginning. As I said, matrix can be anything. We randomize the method. Here, we have a shape assumption that's just tall enough. We have subgaussianity assumption, independence assumption, and bounded density assumption. Some of them can be probably relaxed. I can talk about that. But in any case, we have a model which says that our hyperplanes are, well, not coherent. They are diverse enough. They have independent rows, and they are from reasonable distributions. So Stefan here did, after that, did the work of de-randomizing that. So you don't have to have random model. You can write it for fixed mode. So you can actually express what you need from the matrix in terms of the non-random matrix. What it turns out that for RK, aspect ratio is the same actually, because the extra log was for stochastic gradient descent. That's not an improvement, but all what we need from the model can be expressed in the norm and this restricted small singular value. So it's a worst small singular value over submatrices. And I don't put here rate in the general case because it will be a big expression. So I find it very interesting, this kind of questions, is that you can formulate it as a random model, then you have something nice about the rate. You can formulate it without assuming randomness in the matrix in terms of its spectral properties. Then still to have nice convergence, you still need your characteristics of the matrix satisfy something good, which in particular will be satisfied by this random model. So suddenly these things can give you more models to look at, but still, even when you look at the fixed non-random matrices, you do want to have them nice enough. So you still want to have sufficient incoherence for these fixed non-random random matrices. And the random model is one of the, ways to present it in a succinct way. So it depends. And yeah, I don't. So we do actually, I have it in the next slides. So we do have a block version of that, and we have the same dichotomy. We present both results for non-random and for random case. We have a big formula for non-random case, which depends in a way on like similar quantities, and we have that for random matrix. We have nice convergence rate. So 5 minutes would be enough. 2 minutes should be enough to talk about the proof, because intuition, I gave an intuition already. So our step is the residual. So we don't project if projection was too large. But if projection was not too large, we still can have a good equation, a corrupted equation. If the equation was corrupted, we cannot go too far. When the equation was good, it's like we solve original randomized Kaczmarz, but on the submatrix. And to use the rate for original Kaczmarz, we need the small singular value of the submatrix, which can change from iteration to iteration. We don't know which one of them, so we need this uniform small singular value. And for sub-Gaussian case, it is like for the up to the factor, like for the full matrix square root of m. it is a not hard but nice result, because if you just, so if you take one matrix like that, it's tall sub-Gaussian matrix, so you do know it's square root of m, it's easy, but you don't want to take union bound over all of them. You need to take union bound smarter over the separate rows to actually get that. But so what is interesting here, this is why I have density assumption here. We have density assumption here. This will fail if you have a Bernoulli matrix. So we have a Bernoulli matrix, Rademacher matrix plus minus 1. If you take this structured vector plus minus 1, then you have probability 1/2 to actually make so that first and second coordinate have the same sign, so it cancels out. So on average, you'll have 1/2 of the rows to zero out that. And because you take the worst case, you will always find this worst case submatrix. So that's why we do have this assumption that the distribution is not discrete. And I think it's also a nice open problem here is that, okay, so, and related to what someone told in one of the talks today, that this is the worst case, but it's almost never happens. So because this X has special structure, if you'd like, it has a arithmetic structure, like least common denominator, which is small. And I have a freedom to start wherever, and I'm only interested in the trajectory. So going to potentially quantifying not all the x's, but x's along the trajectory, and the arithmetic structure can also do it for discrete distributions. But if we are interested, like we are not looking, so potentially making the trajectory, for example, randomize the trajectory a little bit to get it out of the bad cases, can just do that for us. Or yeah, but right now, so if you want any x, there is interesting property of this uniform small singular value is that you can have bounded density. Okay, last minute. So what we do here is we looked at all the residuals, so like big subsample, and we did this long pre-processing. As I said, it's long to look at all the distances. Now we said, okay, this is our green trustworthy set, and we just projected onto one equation. We threw away everything else because after we moved, different equations become trustworthy. So we kind of threw away lots of information which we accumulated in this exploration phase. So should we use all the green equations? Can we do block projection on all the equations which we found nice? Actually, this is the case when block projection as is won't be robust. It's exercise is actually a nice example when you can create yourself a case when you never go, you'll be trapped in the corrupted subspace if you do block projection because of the structure, because every block which you have might have one corrupted hyperplane and you stand really there, you never get away. So block projection is not robust, but there are so-called average block methods originally proposed to parallelize blocks. When you do block projection, you have to have it all together. But if you want to parallelize, you probably don't want to do that. And what you can do instead, you can compute some individual projections and then average them. Of course, it's not optimal what you can do with the subspace of the block, but then you can parallelize. And in our case, it means also more robustness because for each individual projection, we know more. So that's what we propose in our paper with Lu Cheng, Ben Jarman, Deanna Needell, and myself. And I should have told that the previous paper is the paper with Will Swartworth, Jane Haddock, and Deanna Needell, and myself, is to average like that. And actually, so what becomes non-trivial and interesting here is that now you know the direction and you don't have, so your step size can be more robust. So it can be bigger, it should be bigger. You have a big speed up here, instead of C over N, you have just C. So it's N times speed up per iteration, and you don't have anything of extra cost per iteration because you already did compute all the individual projections while computing the residual. So you just have free speed up N times with the correct step size. And interesting, I don't have it in the slide, that the step size depends on the coherence properties of the matrix. If it's more incoherent, you have more trust. So basically you define the direction which is better towards the solution than the case when you have coherent matrix. So you can make more confident and much longer and N times longer step sizes. And again, so we can do it for a random model, same model as before. We can do it for a non-random model, and then we have expression something like that. Also depends on the small singular values. This is the same dichotomy as before. Thanks.